Namaskar my dear friends. We have been seeing the basics of AC DC converter in power management design life cycle. So this will be our next part. So already we have seen the advantage and disadvantage of two methods of regulation in AC DC converter method, that was transformer method and switching method, right? So basically these two were circuits. One was transformer method where the input voltage is taken to the input voltage is taken to a lower voltage using a transformer, and after bridge rectifier it actually gets rectified and a regulator will be giving you a desired output, right? So this is how we do in transformer method. However, in switching method the AC input is rectified first, and after that a flyback transformer will be used, okay, and this transformer will again this diode will actually rectify in the secondary side, and this is how you will be getting a smooth output waveform or output voltage regulated, right? And at the same time here there was one thing, that we have to have a control circuit as feedback, which will make sure the switching is done properly. Alright, so now we will try to move out like what is my basics of flyback method, okay? So let us say this is the flyback controller, okay, or this is the flyback method. So what happens is after the rectified output, like after my input voltage VAC input and after my bridge rectifier, we will be getting a voltage which is DC voltage or rectified voltage, okay, after the capacitor. So this particular voltage actually goes into the primary of transformer. So this is my transformer, okay, T1 let us say. So primary of transformer, and this switch which is going to, let us say, Q1, and I'll just name them so that you can understand. This is my, let's say, C2, okay. So and this is my D2. So D1, R1, C1, okay. Now how it is going to work out, that we'll try to see the scope. Alright, so this is my NP, that is number of turns in primary inductor, and NS is number of turns in secondary inductor, okay. Now let us say I have the PWM input to the MOSFET Q1, okay. So in that case what will happen is, this is my gate, this is my drain, and this is my source. So as soon as gate goes high, like as soon as you give a high voltage here from the PWM signal that is going here, what will happen is this transformer primary side will see a closed path, okay. And once it sees closed path, the current starts flowing and it will start increasing. So primary inductor will start getting charged by varying a current. So as you can see, my VGS means voltage across gate to source has increased in T on time, like on time it has gone high. So as you see it is going high, my VGS goes high in on time, then what will happen, my primary current of the inductor or primary side of inductor will start getting high, okay. So this is how it is going high. So you already know that current through inductor is IL is equal to L into or voltage across inductor is L into DIL by dt. So as my current is increasing, you can see IP is nothing but IL here. So your voltage across inductor will start increasing. Understood? So this is how your primary voltage will be higher, or it is going to up to V in. Now as soon as it goes at the same time, you can see all other voltage labels. Let us say VDS. So VDS will be what? Since the MOSFET is on, then drain and source are sorted. So this is how you are getting 0 volt. Understood? Similar to that, in that case there will not be a like secondary current, because at that time the transformer has not transferred its energy. So at that time this current will be 0. Got it? Now let us move to the off time. So as soon as the input goes low, okay, input goes low to the MOSFET, gate of the MOSFET, what will happen? This particular MOSFET will turn off. It means the path is closed, okay. So if this path is, sorry, it is open actually. So if the path is open, then what will happen? It will not start charging, and at that time it will transfer its stored energy to the secondary side. And as soon as it transferred the secondary side, what will happen is there will be a current that would have picked up. So that is nothing but NP by NS into IPK, that is I peak. So that's the current, that is the starting point towards the secondary. Alright. Now since the diode is forward biased, what will happen is this IS current will start charging the capacitor, and it will also start delivering the current to the output load. Alright. And in doing so, this secondary inductor will keep degrading or discharging, and this is how the current in this IS is going down, down, down. Alright. Now same process actually again repeated. As soon as this switch becomes on, again the path is closed, so IP starts charging. So again this IP will start increasing, and this is how VDS becomes 0 and this secondary current becomes 0 in on time. Okay, so I hope you have now a clear understanding of how my MOSFET turn on, turn off is making sure of primary inductor gets charged, then sends the energy to secondary side, and secondary inductor actually charges the capacitor as well as the it delivers the power to the load, and this is how the complete working for our flyback method. Okay, I'm not explaining this one right now. This is the RCD snubber circuit that is used for reducing the ringing that is there at the drain of the MOSFET, or like because of turn off there will be a a fast reversal of the voltage, or a kind of reflection of the voltage. So this goes very high voltage. Okay, so let us say if it has reached to 375 volt, so it can go up to double of that. Understood? So that's the reason it goes around 800 volt or 900 volt. To reduce that spike, we are going to use a suppressor which is called as RCD snubber. Okay, so this we'll talk in detail later on. Now let me give you a proper understanding of how the current flow is there during the off time and on time, so that you can have a proper understanding. So let us say this is a simple circuit that is there, where instead of NP, that is primary side, and NS, that is secondary side number of turns, it is made into normalized form N by 1. Okay, and you know the relation, that is VP by VS, that is primary side voltage by secondary side voltage, or you can talk about V input by V output. Okay, that's nothing to worry about, or V1 by V2. Now what happens is, when this switch gets closed, this MOSFET gets closed, what will happen? There will be a current flowing through the inductor of the primary, that is in blue color. You can see very clearly it starts charging. Now at that time, since the secondary current is not available, so it is 0. However, the capacitor C1 is responsible to drive the load. So this is how only C1 is driving the load. Understood? So when S is closed, this is the path and this is the path. Okay, now when S is open, let's say my switch is open or my MOSFET is open, what will happen in that case? In that case, there will not be current flowing through the primary of inductor. However, the stored energy of secondary side will be transferred to the load, as well as it will charge the capacitor both. Okay, so this is how you are going to get this curve. Okay, understood? So this is all about flyback DC-DC converter. It is written DC-DC. Why? Because you are getting here DC voltage after rectification of from AC, and then from bridge rectifier, and after that you are getting this voltage. That's the reason it is written DC-DC. However, the main aim was from AC to primary side of transformer. Now let us move to the blocks of AC-DC converter that we are going to design. So we have already explained you in our previous sessions. So basically following blocks will be utilized to complete our design from input to output voltage. Okay, So we have AC input, which will be like to, let's say, 230 volt AC. We have safeties, fuses, MOVs, like TVS diodes are also utilized after common mode filter. Then we have safety capacitor like X2 capacitor, Y2 capacitors. They are actually utilized at X1, X2 also, Y1, Y2 also. Okay. So based on the rating, it is considered as X1 or X2. Similar to that, Y1 or Y2. Then we utilize bridge rectifier. So this bridge rectifier actually converts my input voltage, which is in DC, to output voltage, which is going to be what? Little bit of ripples but DC. Okay, so rectified output it will be. Okay, so because of the capacitor, it will be not going to zero, it will be charged, and then it will try to stay in a higher position. Then we have transformer block, which is going to provide isolation between primary to secondary, and also it will actually reduce the, step down the voltage or step up the voltage based on the topology of transformer that is being used. So we are going to use flyback transformer, whose aim is to convert, let us say it is 375 volt here, or 325 volt. For 230 volt it will come around 325 volt. So that will get converted to, let us say, 15 volt output. Understood? Here we have rectifier also. So in the like off time it won't it will be working, and on time it won't be working, like it will provide a blockage path. And then we utilize some filters and like inductors and capacitors, so that we can filter out the output to have a better smooth output voltage. To regulate this output voltage to a desired position, we try to use a feedback circuit where there will be a resistor voltage divider circuits that can be giving you a reference voltage, and that is actually like taken through a TL431 or any reference type ICs, and then through a optocoupler it is fed back to the controller, which is having right now here inbuilt MOSFET, and this is how it will try to control the transformer switching, so that it is a closed loop system which is making sure to give you output voltage as desired one. Okay, so I have listed down all the parts that is going to be like studied in this particular session. We have like AC input, then we have fuse and transient suppressor like MOVs, then we have safety capacitors. Okay, then we have common mode filters, then we have bridge rectifier, we have bulk capacitor that will be used to store the charges and smoothen the output of bridge rectifier. Then we will be using RCD snubber to suppress the ringing and like reflected very high reflected voltage. We will be utilizing transformer. Okay, so these are the like blocks or steps that we will be doing. More are there, which are like controller ICs, which will be used to control the MOSFET switching characteristics, and we have output rectifier, like secondary side we will be using one diode. Then we have filters and capacitor at the output side. Then we are going to utilize our voltage reference and feedback circuit to regulate the output voltage to a desired output level, and optocoupler will be giving it back through isolation to the primary side of PWM microcontroller, PWM controller. Okay, so this was all the like paths that we will be like taking up from beginning to end, so that we can design complete like AC DC converter that we have to have in our hand. Okay, so after learning each of the block, we will be able to design this particular circuit, as I have told you in the previous session, from beginning to end, and there will be like part selection in the meantime itself, so that like we can have an understanding of how to select the parts for what rating and what values, everything. Okay. Let me give you a proper understanding of feedback. Okay, so let us say we have output voltage here V out, and let's say we'll just take an example of 15 volt itself. So our aim is to put a voltage division here. Okay, and this is going to produce a output volt like reference voltage that will be given back to the feedback. So how do we design that? Okay, so let us say we have 15 voltage will output. Our aim is to utilize, let us say, TL431. The reference voltage for this is actually 2.495 volt. Okay, 2.5 volt, but we keep 5 millivolt down. Now our aim is to identify what is my R1 and R2 so that it can get excited and it can give the like this 15 volt cathode to anode, VKA cathode to anode, to the optocoupler, and optocoupler will transfer that voltage level to the feedback. Understood? So what is going to happen? My voltage KA, like VKA, which is desired, is how much? 15 volt output. So same way you can design the same resistor R1 R2 for other voltage level, let us say 12 volt, 24 volt, and whatever voltage level of output that you want to have, you can utilize this thing. However, this TL431 can be used only from 2.5 volt to 35 volt or 36 volt max. Okay, so more than that rating output you don't use this TL431. Okay, now our aim is to see what would be the voltage at this particular place, VK. So VK is going to be how much? Is V reference into 1 plus R1 by R2, and V reference is 2.495 volt, as I told you. Let us consider that my R2 is 10 kilo ohm. So in that case what will happen? I'll put down the values. Vk is going to be equal to 2.495 into 1 plus R1 by R2, that is 10k. By solving this, we are going to get how much? 15 by 2.495 will give you 5.012 minus 1, right? So that is going to give you 5.012 all the things, and R1 is going to be equal to this multiplied by 10, so that is 50.12 kilo ohm. Understood? So we have found out the value of R1 and R2. Now if you want, you can see what is the total amount of current that is flowing in this branch. That is nothing but the voltage divided by total resistance. So that is 15 by R1 plus R2, that is going to be 0.249 milliamperes. Okay, I will tell you later on like what is the criteria of choosing this, like a value not too high or not too low, because see, even if you consider 100 kilo ohm, then also you will get a value of R1 to be some other values. So but in that case the current Ix will be very less, so it may not be able to excite the reference of this particular TL431. That's the main reason. Okay, so during the TL431 explanation we will try to understand what is the range of resistors, or what is the range of current that we should be designing so that this particular excitation happens properly. Okay, now let us start with flyback topology. So as you can see, this is a very simple flyback topology. So we have the like a voltage from the capacitor, or after bridge rectifier, this is the bulk capacitor, and it is supplying to my like primary side. So let us say we have NP and NS, or we can consider it as N is to 1. Okay, so in normalized form. We have MOSFET which is acting as a switch, so that it is giving a path during on time and switching off the path during off time. Okay, so this is my PWM. And output side we have half wave rectifier, which is actually transferring helping to transfer the energy and drive the load C2 and RL. Okay, so if you see, if you want to derive the expression for this particular like flyback topology, then what will happen is let me give you an understanding of, let us say we have the like a transformer as N1 is to 1. Okay, or N is to 1, N is to 1. Okay, and let's say this is my D1, this is my C1, and this is my RL. Okay, and this is my C1, this is my Q1. Now what happens is at T1 is transformer. Now what happens is, for on condition, when this guy is on, because of the this just now we have explained, like when is on, so this is my on time, this is my off time. Okay, and this is the total period T. So what we'll do is, for on condition, for on time, what would be the total energy input? So total energy input to the primary side will be energy input. Energy input is going to be V input. Let us say the input voltage that is flowing here, like V input, multiplied by how much time it has entering. So V in into T on by N, okay, where N is your turns ratio. Now what will be off time? Like for off time, how much energy will be sent out? So that is your energy transfer, energy out. So this energy out is going to be your V out into T off by 1, because I have considered it as N by 1 or N is to 1. So you can see N is to 1 is nothing but NP by NS or N1 by N2 is equal to N by 1. Like that we have considered. Okay. So this is all. Now if you try to understand that my energy input must be equal to energy output, okay, so in that case what will happen? My energy input is going to be equal to energy output. It means my V in into T on must be equal to V out into T off, and this T off can be written as T on T minus T on, like total time period minus T on. Okay. Now from here we can find out my V output by V input is going to be equal to, what is that? V output by V input is going to be equal to T on by N in divided by this one, right? So it will be, let us say, 1 by N into T on divided by T minus T on. Got it? Now if you divide it by T all the sides, then we can write it down as V output by V input is going to be 1 by N and multiplied by T on by T divided by 1 minus T on by T. So I have divided numerator and denominator by time period. So this is nothing but, just now I told you this is a duty cycle, which is T on by capital T. So that is going to give us my V output expression as V input into 1 by N into delta by 1 minus delta. So this is the final expression for your output voltage that you will be receiving, and here I have considered the efficiency to be 100%. Okay. So while deriving the expression that has been taken into account is efficiency is 100%. Okay. Now let us move to understanding of how our different circuits are designed. Like I told you just now that how this snubber circuit will be utilized, or how we are going to design our feedback circuits and all these things. So what we'll do is we'll try to take these concepts into our next session. Thank you so much.